and I'm like overwhelmed by this turnout today. So thank you all for taking time out on a Saturday and coming. I'll just very quickly introduce us and what we are doing here. But before that, some I say housekeeping rules. So if you go out of this room and take a left, at the end of the corridor, the bathrooms are to your right and the cafeteria is to your left. Coffee, biscuits, everything will be available there. After the session is done, we'll have some time to just get coffee, have something to eat, chat. But if anybody really needs a dose of caffeine right now, we'll be starting in about 10 minutes. So if you want to go and grab a cup of coffee or use the facilities, you're more than welcome to do that. If you go out of this room and go straight, there is some room that like triggers an alarm. So please don't open any doors there. Just be a little careful. Otherwise, I feel like some emergency services will show up. So let me just tell you a little bit about Women Who Code. This is a global organization. We started the Mumbai chapter in 2019. Shaina and I started it together. She's one of the other directors. We have a third director, Tanaya, who's not here right now. She's doing a master's in linguistics in the US. I can maybe very quickly introduce myself and then hand it over to Shaina. So I have been working in tech my whole career. I have worked in various technologies. I work a lot in the health tech space. I work with 3D printing. I work with blockchain. I've actually very recently joined a company as a co-founder. It's a women's health company, and we're basically using AI to make reproductive health accessible to everybody in India. So AI plus doctors to create a solution like that. Very excited about it. I love it. So if you are interested and want to learn more, come tell me. I'm also building a team, so junior and mid roles. So it's new and I'm like in full honeymoon phase right now. So please come talk to me. So with that, I think I can maybe just hand it over to Shaina. Shaina is actually an economist and has a very interesting journey on how she learned how to code and kind of embrace that space. That's really inspiring. But I'll just hand it over to her to give you maybe a 10-minute introduction of Women in Code, and then at 11:30 we'll start with the main event of the day. But before we start, any questions from anybody at all about anything? Okay, great. I just have one request in terms of the presentation. We are very welcoming of questions. We love questions. So I mean, the idea is to learn something new, and it's the best way to do it is by asking questions. But let's limit that to questions. If you have things to add to the presentation, or if you feel like there's something missing or a different opinion, maybe find Kartika at the end and chat with her about that. Because the goal of today is to learn from her. Thanks, Shaina.
Yeah, thank you. All right. Hello, everyone. Good morning. We're very excited to see all of you here. Thanks for making time on a Saturday morning, when on a weekend, and sharing that with us. We really appreciate it. So a bit about Women Who Code and also about the event. So this is a very beautiful and happy photo of our community at one of our events. And this is usually what our events look like. And we host a number of events across a range of topics across the year. So we're looking forward to seeing you in the future as well at our other events. The mission of Women Who Code is to empower diverse women to excel in technology careers. And we essentially want to see women in a whole range of roles, not just as software engineers, but also, let's say, as the head of a venture capital firm, or maybe as a data scientist, or anything that interests anyone in this community. And our vision is a tech industry where diverse women and historically excluded people thrive at every level. Our values are that we focus on the mission, we design for inclusion, we advocate for change, and we focus on the journey forward. We have a code of conduct that we stick to very strictly. Women Who Code is an inclusive community dedicated to providing an empowering experience for everyone who participates in or supports our community, regardless of gender, gender identity and expression, sexual orientation, ability, physical appearance, body size, race, ethnicity, age, religion, socio-economic status, caste, creed, political affiliation, or preferred programming languages. So if you have any questions, feel free to reach out to us. You can also reach out on these URLs that have been shared. So a quick overview again of our community. We have approximately 343,000 members in 147 countries. It's a very big and thriving community, so please make sure that you have also signed up to join. We have pasted QR codes across the room, so we'd be very excited to have you come and join our community. And when we talk about representation, it is both at a global level, but also at a local level. So at a global level, you can see the mix of representation and the different communities that have been included. In case anyone has any comments to make on that, that's fine.
No, so something that I love about this slide is that it's just interesting to look at and see that the white community is 26%. And the East and South Asian is 34%. And this is an indication of the change that has already been made, right?
Yeah.
Like this is like the global community of women who code, and this is a representation of it. So it just makes me really happy every time I see this slide. I'm like you can see very, very really that change is happening.
Yeah, absolutely.
Yeah. So see, this is like Women Who Code has done some sort of research, and they have figured out that women tend to leave technology careers at various stages. You know, like either they don't enter, so you are interested in technology as a school student, but you don't study it in college, or you start working in a couple of years, you leave. Or getting married and having children are like very common drop-off points for women. But if a woman stays and keeps working, you can add $1.7 million to her lifetime financial value. Now this is a US number, so let's bring it down for India. But even then, right, even if we account for purchasing power parity and lower salaries and everything, just looking at this room here, if we are able to keep every single one of us in tech, working, not leaving our jobs, all the women in this room, that is more than 800 crore in this room today of just the women. And that is why this community exists. That is why we are all here on a Saturday morning. Because you're adding that value to each of our lives. You're adding that value to each of our families. You're adding the value to the GDP of the country, right? That's the impact that we are having. And that's why we are all sacrificing our Saturday to be here. That is what success looks like. Is to make sure that everybody stays, everybody keeps working. And we are all able to be really financially independent and successful together.
Yeah, that was very nice. Thank you, Akansha. And a bit more about the Mumbai chapter. Another very cute, beautiful, happy photo of us at an event. Like Akansha had mentioned, we launched in 2019. We've had approximately 15 in-person events so far, and we're looking forward to many more. This is an overview of the directors, Akansha, me, and Tanaya. We have leads, so leads look after certain tracks. We have tracks that focus on specific areas of technology. So say for example, Android or cloud technology, data science, AI. Those are all separate tracks because some people are very focused on just a certain area of technology and they don't want to focus on everything. So if you approach the lead of a certain track, they can guide you on your way forward. If you ask them questions on how do I begin learning cloud technology, how do I begin learning data science, I'm interested in being a data scientist, they can guide you on your way forward. So these are our leads. Disha is the lead for Android technology, Prachi is the lead for cloud, and Renuka is the lead for backend technology. And that brings us to our event today. So Women Who Code is very honored to have Kartika speak to us today. The event is Neuroscience for Coders, and we're very grateful to Microsoft for allowing us to be in their office and to have coffee and tea while we listen to Kartika and also engage in some quizzes. Another thing we do at Women Who Code is something called Applaud Her. So people in the community usually share some of the highlights that they've had in their career recently or even in their learning journey. So I'm curious to know if anyone here has any achievements that they want to share. So it could be not just at work or if some of you are in college, then at college, but maybe even in your personal life. So if anyone wants to share anything? Okay, I have a small one on behalf of Kartika. So Kartika has been accepted to a PhD program, so it's a master's program. And Kartika, do you want to talk about it a little?
Yeah, sure. So I was like, the poster says I'm working with fractal analytics, but it was until last week. I am now next week going to UK to pursue masters in this field, computational neuroscience and cognitive robotics. I've taken the past 5 years to really figure out, what I'm really interested in. Finally, I'm going for this master's, and then I'll be doing a PhD as well. So yeah, that's my new chapter going to be.
That's amazing. And I have another applaud her for Akanksha. Akanksha has already spoken a bit about it, but I don't think she mentioned the name of the company. So I want to applaud her on taking up this role. But Akanksha, do you want to speak more about the company and maybe mention the name and more details on that? Yeah.
Sure. I spoke briefly about it, but I just started as co-founder at Pinky Promise. We're a digital clinic, so it's an AI plus human hybrid solution to make reproductive health care accessible. So currently, most of our patients in our target market is tier 2, tier 3 cities of India. And the idea is that 24/7 you can come and start a consultation for any reproductive healthcare issue. And the AI does most of the work and then shows it to a doctor. So we have doctors on our staff, and then they review it and they send out a prescription. So within 5 minutes, you can get a prescription and kind of start your care. That's what we're doing. I will not take up more time. I've already spoken about it. So,
Are you
Yeah, she's from my school. Yeah, she's a founder.
I know. I mean, I don't know her directly, but
Okay, well, does anyone have anything to share about themselves? Alright, so now a bit about Kartika. So Kartika was a researcher at Fractal Analytics in their cerebral team. She works at the intersection of neuroscience and AI, and in the past she has also worked as a software engineer, a data scientist, and a consultant. And it is this exploration that has made her realize her true passion in research involving computational neuroscience. So apart from this, you can also find her attending dance workshops and posting dance reels. Very cool. We're very happy to have you here, Kartika. If you want to add anything to this,
I think we'll take time towards the end of it and just have a chit chat. Yeah. Because it was a really nice introduction. Yeah.
No, I'm just saying that we'll now move on to the main presentation, but if you guys want to just take a couple of minutes, coffee, anything else, if everybody's good to go, then we can just start.
Yeah.
Good?
Because I think we'll take a break in midway of the session, maybe that can also
Or we can take a break and you can finish up and then we can do a networking.
Cool.
session.
Yeah.
Okay, great.
Woo! So I'll just set this up and then we'll get started. Okay, thank you so much everyone for coming today. And really thanks for having me here, Shaina, Akanksha. This is a really good opportunity for me because what I have to share with you all today is something that I'm passionate about, and it's the last 2 years. I started as a fresh, a beginner in this field, and I've really started learning and understanding what is this all field about. So what I'm sharing you today is the condensation of the entire 2 years of journey that I've had in this field. And I will be more than open to feedbacks because this is the first time actually presenting this topic here, and that it is with Women Who Code Mumbai. So before, I'll just set up an agenda. I know the topic is neuroscience for coders, and I kept it coders because I wanted it to be generalized. You are a coder even if you're an AI professional, you are a coder even if you're a front-end developer. So I kept it generalized, and the idea is I want everyone from this crowd here to take away at least one thing from the session. And because I am coming from an AI background, I have more to say from the AI point of view. So like almost half of the session, or maybe a little more than half of the session, will be more towards the neuroscience and AI relationship. I'll be making it very simple for all of you to understand. But the second half of the session will be more generalized in terms of what other things neuroscience and tech can do in synchrony. Okay, so that's the agenda for today, and yeah, so we'll have few activities also in between. There'll be quiz, and so yeah, for that, what I'll need you is to. I hope everyone is connected to internet on your mobile. If not, there is Wi-Fi here. I'll share a link and a code. So, okay, we'll get there when we come to that particular quiz. But you'll have to just sign up and put your answers, okay? So that is going to be one type of an activity. The second activity is going to be where we will be. Okay, I'll explain when I come there. But yeah, just be aware there's going to be activity. It's going to be an interactive session. So I want you all to really participate in this talk, okay? We'll do it together. Let's start, and I always love to start this topic with an analogy, and that is, you know, long back during the Michael Faraday day, right? That time magnet was there. People were using magnets in the form of compass and all of that, but no one really knew how it really functions, okay? So it was Michael Faraday who started doing a lot of experiments with magnets and try to understand, okay, what is happening and everything. But it was still at the very experimentational, you know, that level, okay? It was much later when Maxwell came into picture and formalized the entire field of electromagnetic. You know, we have electromagnetic wave theory and all of that. So now it is more generalized. When you have sort of equations, you kind of understand the general principle of this entire field, right? When we compare that to neuroscience, we are still at the Michael Faraday stage. We have not seen the stage yet. There is no general principle of brain that we know. It's still debated. Everything is debated. So isn't that very exciting to be in this stage where, you know, there's so much to explore. There is no right, no wrong answer. Today this will be debated, tomorrow something else. So I think we are at the cusp of something really exciting happening in this field, and I am really inspired. I hope you all are also going to get inspired by this field. And having inspiration is one thing, but the second thing is you will learn only and only if you have a feeling of ignorance within you. If you have this attitude that, oh, I know this, I know that, you won't learn. You need to have more questions. That is how you'll build this feeling of ignorance. So this is going to be your first activity, wherein throughout the session, I want you to, you know, just form connections and just keep thinking about the kind of questions you want to answer. So the more the questions, the more the curiosity you have, and the more ignorance and more you'll learn. Okay, so this is a practice that we used to do in our team when I was working in Cerebral, that we always began any brainstorming session, any new topic with a set of questions. And that kind of shows us that, okay, there's so much to discover, right? So this is going to be an activity. I don't know if there are post-it notes, but if not, on your notepad, just make notes of questions. And the questions can be literally anything. Like, for example, how can AI do multitasking like the way humans do? Like random questions, can be basic, anything, okay? So make a list of questions, and towards the end of the session, we'll just share a few questions that we have. So maybe everyone can take out at least minimum 10 questions from the session, okay? So that is your first activity. We'll get to that at the end of the talk. Now when I begin, I would like to share the history of the field of neuroscience and AI. And so when so like you'll see from history that this field of AI and neuroscience has always been, you know, going in parallel. And somewhere down the line in the recent past is where that disconnect happened. But we'll see how it all started. It goes back to 1943 when Matlock and Pitt, they came up with this neuron model, which is basically an electronic brain. So they realized that the neurons inside our brain, they are just binary, like they just either spike or don't spike, all or nothing. And that idea, they put it into an electronic brain. And electronics, we know there is AND gates, OR gates, NOT gates, all of that. These are the basic units, right? So for example, in the case of AND gate, the two inputs x and y, if both of the inputs are 1, only then the output will be 1. Otherwise, all the scenarios, it is going to be 0. That is the AND gate, right? So, how they made it into an electronic brain is that they added this particular thresholding unit, and in the input, they have weights. +1, +1 and -2. So this additional is basically a biasing term. So if you give 1 and 1 as an input, then this sum, it's a weighted sum. So x into 1, y into 1, and -2. You add it up and you see the threshold. If it is positive, then the output is going to be 1. If it is negative, then the output is going to be 0. Positive or 0, then the output is going to be 1. So if it is 1 and 1, it's going to be, the sum is what? 0, which is going to be 1, yeah. So if you take any other example, 0, 1, 0, 0, you'll see the sum is going to be negative and the output is going to be 0. So that's how they constructed the AND gate. Same way they constructed OR gate, NOT gate. OR is basically when x and y, both, either of one is 1, then you'll get an output of 1. So if you see, it's going to function, same way NOT is just reversing the sign, right? Or, I mean, 1 will become 0, 0 will become 1. And the weights here, it was more like a trial and error to just come up with these weights. So this was the simplest and the very first artificial neural network in a way, which is the electronic brain. Then somewhere in 1957 came this thing called perceptron. Now, this person called Frank Rosenblatt, he is a very key figure behind this discovery of perceptron. It's actually an improvised version of the thing that we saw previously, which was McLaughlin's neuron. And here, what happens is, there is no rule that the inputs should be either 0 or 1, it can be any number. And it's again going to do the same thing, weighted sum of all the inputs. There is going to be a thresholding, and you get an output based on, if it's above the threshold, it's going to be 1, if it is below, it's going to be 0. Those are the equations. If you understand, it's okay, otherwise don't worry. But here, the improvement was that these weights, W1 to Wn, along with the theta, which is the threshold, is learnable. So by learnable, what I mean is that you can see, you can just do a linear equation. You can solve linear equations. Let's say there are only 2 weights right now, only 2 inputs. And there is this theta, which will be the third weight that we need to learn. So you'll form these equations like x1 into w1 plus x2 into w2 plus the weight theta equal to 0 if if the weighted sum is greater than theta, then it is going to be 1 output, otherwise it's going to be 0. So these are just, you can translate into linear equations, and you can just solve it the way, you solve linear equations. And you get the answers for these weights. So there came this idea of learnable, and that kind of triggered a lot of new interesting things for people to discover, because the whole idea that learning comes into picture. Then you can make that electronic model learn a lot of new things just by solving these weights or linear equations in a way. Is it clear so far? Okay, so after that, in 1969 is when the start of AI winter came into picture, and that was triggered by these 2 people called Marvin Minsky and Papert. So what they did is they studied the entire perceptron in great detail. They even wrote a book called Perceptron, and in that they have explained why perceptron is not going to work. And it's because it's just capable of solving linear equations. AND gate, OR gate, if you see, AND gate is what? Only when both the x1 and x2 are going to be 1, it's going to be getting activated, otherwise it's not going to get activated. And you can use a linear line to separate these 2 categories, which is nothing but this line. If you see, the equation of the line is going to give the weights, W1 and W2, right? So even for OR gate, you can use a linear separable line. But in the case of XOR gate, which is, it's going to get activated when both the input are same. So, both the input are different. So 0, 1 it will get activated, 1, 0 it's going to get activated. and the other, if both inputs are same, it's not going to get activated. But there is no linear line that you can, use to separate these categories, right? You'll have all the curves to separate it. So that was a challenge faced by the perceptron model cannot solve this because the linear, it's basically learning characteristics based on linear equations. So they wrote the entire book and everyone kind of understood, okay, this is just a hype, it's not going to work out. And there was an AI winter, which is basically no research happened in this field. It just began and went down, no funding came, nothing. So it was later lifted by our own godfather of AI, Geoffrey Hinton, along with 2 others in 1986 with the discovery of multi-layered perceptron. Now, what is multi-layered perceptron? They again went into the brain and they realized it's not just one neuron that is working, right? There's network of neurons. So let's just put networks of neurons here also and try to see if we can solve equations. And with that, they could solve the XOR problem. So instead of 1 neuron, they added 2 more neurons. And what happens now is with the first neuron, they can separate these 2 parts. Second neuron can separate these 2 parts. And the third neuron is basically separating this part with the other part. That way. And you get the XOR problem solved. Okay, so that was one. But again, the challenge is, this is still fine, we can still solve equations, maybe it will be 10 equations or something, but we can still solve. But if these neurons start increasing, how can we solve so much, equations, right? So there was a challenge of how do we make this entire thing learnable again? And that's when the entire optimization algorithm came and the well-known backpropagation algorithm. So they wrote a paper which was like a really amazing paper on backpropagation around the year 1986, and they found the error, and the error was backpropagated. Like gradient of the error is backpropagated and the weights are altered. So that is how even a huge network can learn the weights now. And with this discovery, again funding started coming in and they realized, okay, now we can still work with neural networks. So that AI winter period was over. But again, there was a challenge. We'll come to that because here is summary. Just going back, 1940, we had electronic brain, then we had perceptron by Rosenblatt, then we had Adaline is also one type of perceptron in a way, then XOR problem. So this period was a golden age after perceptron. Then we had the dark age, which is the winter, which was, the key figure is Minsky, he is cursed for that. And then we had multi-layered perceptron, David Rumelhart, Geoffrey Hinton, Ronald Williams. These are the key figures behind multi-layered perceptron and backpropagation. And after that, there was again a push for neural networks because they realized this is going to work when we have like huge GPUs and data sets and all of that. So that time it was not there. So which is why there was not much of an application of neural networks, and again it kind of faded. And that's when SVMs and all these kind of algorithms took off. But later on we have all those data sets available, and we also have compute power, everything. So again, neural networks are back. There is transformers, there is now everything, like everything is just neural networks. So that's the history. And now I will have a quiz. So just go to slido.com and enter this particular code. I'll write the code on the whiteboard.
Does anyone need post-it notes? We have pens and paper. Yeah, I'll help pass them around. Anybody else? Could you raise your hand? Yeah, what do you need? Thank you. If there aren't enough pens, please share. Ask the person next to you. I'm sure you'll be kind enough to send one.
Karthik, I can't see the question.
Yeah, I'll start. Launch the quiz.
Share the pen.
Everyone logged in? Can I launch the quiz? Yeah.
Is everybody logged in? Anybody not logged in?
Hey folks, reply with a yes or no.
The code is written here. 3274089. I can see 13, 16. Okay, the count is increasing. 17, 24 people are there. 26.
If anyone needs help logging in, we'll walk around and help you. You want to raise your hand?
How many people are there in this queue?
About 80.
80. Okay, we'll wait for the count to be.
Do they need a pen?
We'll start the quiz.
Is everybody in? Anybody is having trouble? Please raise your hand. Otherwise, we'll start the quiz.
So you can see one question. It's only one question right now. What do David Rumelhart and Geoffrey Hinton have in common? We saw these two figures, right? So yeah, and it is a multiple answer quiz. So one or more answers are correct in this. Yeah, 10 seconds more. Just finish up your answers. All right, let's go to the result. Everyone has got one answer very, correct. So you all are saying backpropagation, they both came together with us. That's correct, obviously. And the second answer, which is correct, is they both graduated in psychology. And godfather of AI is only Geoffrey Hinton, not David Rumelhart. So here, when I realized both of them did their bachelor's in psychology, it was like a wow moment for me, because I realized, okay, these people are computer scientists or something, But then the basics is brain. They're studying the brain, and that's how they're able to really come up with these algorithms. So this kind of tells us that, just by learning about computers and everything is not enough. If you have to be ahead of the curve, you need to know also brain, how it really works, because that is the origin of all this algorithm. Okay, so we'll go back to the presentation. Let me start sharing the screen again. So now what I'm going to do is, I read this book last month, actually earlier, by Mark Humphreys called The Spike. I took a month to read this, an epic journey through the brain in 2.1 seconds. So this entire book is just describing the 2.1 seconds of processing which is happening in the brain, which I read in 1 month, and I'm going to share the condensed form of it in 10 minutes for you all. And with this, what I want to do, it's more like a story that you're going to learn about how the brain really works, the neurons in the brain, what kind of neurons are there, how is it all happening, so that then you can draw parallels between how AI algorithms are really working. And the second part, when we start drawing the parallels between AI, you will be telling me that, okay, this is how the neuron works, this is how AI is working. Okay, so that's how we're going to do. So the first part, let me take you all through how really the brain works. Begins with a neuron. Neuron is a cell which has these dendrites. This is the input. And the signal from the input, that is the dendrite, passes through the cell body through the axon. Axon is the output. And there are other things, myelin sheath, all of that is important, has its own role. I'm not going to detail, but it just kind of helps in passing the information over long distance. So this is the neuron, okay, and it has ion channels. So neuron has these sodium ions concentration more, and like basically it's all chemistry there, where when two neurons communicate, which is the presynaptic neuron, that is the first neuron's axon, will send signals to the postsynaptic, which is the second neuron's dendrites, and this junction is called synapse. So this synapse is basically where the first neuron, presynaptic neuron, will pass the neurotransmitters and communicate the signal. Okay, so this is a neuron in the brain. Okay, and what happens is, how does it spike? Its resting potential, like when nothing is happening, is minus 70 milliwatts, and so it's there. And say at a particular time point, there is a signal that it is getting, and that signal goes above the threshold. And let's say for this particular neuron, minus 55 is the threshold. So when it goes beyond that threshold, there is a depolarization that is happening. Again, that is nothing but the negative charge inside the cell is going down. So more of sodium ions are coming inside the cell, and it's getting more of positive charge. Okay, so that's what is happening, and its depolarization is happening, and it reaches the action potential. That is basically a spike. So if a signal comes which is less than threshold, nothing is going to happen to that neuron. Only if it goes beyond the threshold, there is going to be a spike. It's all or nothing. And then after a sudden spike, it comes down, and when it comes down, it can't go into another spike very fast, right? It needs a cooling period, the refractory period. So there it goes down, and then again it comes back to resting state, which is basically it's ready to spike again. So this is how it spikes, and in case the threshold is not reached, nothing is going to happen. It's just going to continue staying in the resting state. Yeah, but there are like other neurons also which don't need spikes to really communicate, which is like in the retina and all. We are not going into that, but in general, this is how neurons work. And even when I said the information goes from dendrites to axon, that is also not general. There are few dendro-dendrite connections also, where dendrite can directly communicate to dendrite. I'm just telling you exception, but in overall, it's dendrite to axon. Okay.
So, I'm sorry,
Yeah.
action potential, what does that lead to?
It's a spike. So then,
spike would be like information is getting passed.
yeah. So it is
Okay.
so in that junction,
Sure.
when the spike is happening, the communication has been transferred
Okay.
from the first presynaptic to postsynaptic
Yeah.
neuron. Yeah.
Otherwise, there's no communication,
No
that
communication.
happens.
Nothing. Yeah.
Okay.
So this would mean that neuron has fired, right? That
Yeah.
particular neuron
Yeah.
has fired. This means.
Yes.
Yeah.
Yes. Exactly. Yeah.
So it doesn't really connect with like action in the sense of the human action that we're doing. It's just the
At the
neuron.
basic level, this is what is leading
Sure.
to it. Yeah.
Interesting.
Yeah.
Very, very interesting.
Okay, so, and in neurons also, now this is another interesting thing. When I got to learn about it, I was like, wow, because it's always not a spike that is leading to communication. See, if you see one neuron is activating, it's activating another neuron, it will just go in a chain of activation, activation, your brain will collapse, right? So it also needs inhibition. And that's why there are two types of synaptic communication that is happening. One is the excitatory, the other is inhibitory. And the change is due to the neurotransmitter. So glutamate is an excitatory neurotransmitter, GABA is an inhibitory neurotransmitter. And what excitatory does is increase the positive concentration inside the cell. Inhibitory increases the negative concentration inside the cell. So this is depolarization. That is hyperpolarization. So the voltage goes down. But although there are more of excitatory, like 90% neurons in the brain is going to be excitatory, only 10% is going to be inhibitory. But that 10% is strong enough, like more strong than the excitatory ones, to really balance the excitatory and inhibitory thing in your brain. So that is how your brain is, kept into this Goldilocks zone where it's not that active, not that quiet, it's just right with this balance that is maintained by excitatory and inhibitory neurons. Okay.
So SSRIs would be here.
Sorry, what?
Selective serotonin receptor inhibitors would be
Yeah.
here.
Yeah.
Okay.
Okay.
SSRIs would be inhibitory or excitatory?
So
They
I
need to, sorry.
yeah,
No.
you can go ahead because I myself won't have a clear answer to it.
No, I mean basically they're more towards depolarization because the name isn't really, they're not inhibiting the absorption, right? They're just letting more of this whatever the positive charge
Yeah,
or whatever.
sodium, yeah.
I mean that's my understanding. What do you think? I don't know.
So obviously it's a neurobiologist who can someone who is specialized in the brain
Sure.
who can answer it. I'm
Yeah.
from AI background. I just pick up few things that I can understand.
Sure.
Okay, but if you are coming from that background, I would really like to know the details of it.
Yeah. No, it's interesting for sure.
Yeah. Okay.
I'm also from AI background, but I have a little bit of
No, okay, great. I know serotonin because obviously it is you're happy or it's going to act
Yeah.
more. It's more of activating
Exactly.
things.
It seems like more
Yeah.
like an activating.
Yeah.
It seems like the first, not the inhibitory.
Yeah, it is generally going to be excitatory. That's my understanding, but I don't want to claim it
Yeah.
in case it's wrong.
Yeah, we can check.
Yeah.
Because it has inhibition in the name, but
Yeah.
actually it's excitatory.
Yeah. Okay. So yeah, having said that, we also should know that neurons are not deterministic. They are very random. If we say that okay, it's the threshold. If the threshold reaches, it's always going to spike. That is deterministic, but actually it's random because we saw they are both excitatory and inhibitory, right? So all sort of connections are coming to its dendritic tree to this neuron. So sometimes excitation will be there, sometimes inhibition will be there for the same kind of input that input signal that it's seeing, like whatever we are seeing for the same thing. It can sometimes excite, can sometimes inhibit. So it's like happening like this, and only when it's like exciting that can spike. Sometimes that might not happen, it will be instead inhibited. So it's very random. It's not deterministic. Even though there is a set threshold, it's very random, and that might.
Sorry to interrupt. So you're saying even for the same inputs, right? So
Yeah.
then if we compare with the AI, where we have a deterministic, if we are giving these weights, these inputs,
Yeah.
it's always going to be an exact output.
Exactly.
All we're saying, in spite of that entire combination of same inputs coming in, we may have an inhibitory, excitatory, or a flat response. It
Yeah.
is not.
Yeah.
So this is more in line with a pre-trained model.
You are already making connections.
Okay. Yeah.
Yeah. But yeah, hold that thought.
Yeah.
I mean, really interesting discussion because so it's not deterministic, it's random, and why the synaptic failure is necessary is because two things. One, it helps dynamically adjust the reliability of the neuron. So this target neuron, which is getting a lot of these inputs from different neurons, which is basically the count is not tens, it's 7,000s. So many neurons are contributing that one particular neuron, okay? So it's dynamically this target neuron is trying to understand, okay, what is the redundancy in my input? What is the, again, brain is very energy efficient, right? So it doesn't want to waste any energy. So it will shut off all the synapses which is redundant. So this target neuron is going to understand, okay, what is the redundant? Even though it's coming, it's going to shut it off because it's not necessary, right? So that is why synaptic failures are helpful to increase the reliability and also to avoid overfitting. which is like that kind of helps us to learn. If we have learned one thing thoroughly, something new comes, we might find it difficult to learn it, right? But in case we know, if you're master of that saying, right? So if you know everything little, then maybe we are very flexible to learn new things. So that's how brain also works. It doesn't want to overfit. So the synaptic failure, this randomness kind of prevents that overfitting nature.
So is this something, again, sorry, but is this something, so then we are constantly in a learning phase, or what we call neuroplasticity?
Yeah.
Where there is this possibility of this connection changing, or the
Right.
way it's changing and all of that. Is this because of this part or no?
Yes, it contributes. It's a small concept in that entire huge concept, neuroplasticity. But yeah, it contributes. Yeah. I have a slide on that towards the end. Yeah. Okay. So moving on, we saw the spikes, like voltage spikes, right? He hits the threshold, it will spike, not spike. But there are two types of, in fact, more types, but these are the two ones that are discovered, which is timer neuron and counter neuron. So timer neuron is basically, it will spike when the delay between the two input signals is within the threshold, above the threshold, like basically within the threshold. So if the two spikes are, the input that it is getting has a particular time delay, it will spike, it will otherwise not spike. That is how it functions based on the time. And this timer neuron is going to be more visible closer to the sensory system, like the neurons which are very close to the eyes, the retina, right? They are going to be coded more from the timer perspective. And the other neurons which are like inside the brain, which is more in the cortex level, they're going to be more of counter neuron. That is basically, it will count the number of spikes that's coming onto its input. So the more the spikes, it will spike. Otherwise, it will not spike. So there are two types. Timer neuron, that is there's a reason behind why they are seen more in the sensory, because sensors, the timing is more important, right? That's why timer neuron, and counter is how strong is that signal. So counter neuron.
So in timer neuron, if there is a delay between two signals, then only it will spike.
Yeah, so there should be a particular delay. If the delay is there, then it will spike. Otherwise, it won't spike. So when we are perceiving something also, only if that change is happening within a delay we can understand. Otherwise, we can't understand it, right? Yeah. So it's all coded down in the neurons.
Is it similar to what we do in computer science, like debouncing and throttling?
Can you explain that a bit?
So debouncing means, so for example, an event is fired, so we wait for like the user stop for X milliseconds, and then we'll fire the event.
Right.
Same with throttling, like we only allow 10 events in a minute.
Yeah.
So is it similar to like that?
Definitely, the concepts are parallel there. Yeah, makes sense. Okay. So now I have another interesting thing, dark neurons. It's very fascinating to know that all these parallels that we are drawing between AI, why are you doing a laugh? Something?
No.
Okay, cool.
Share the joke with
Yeah.
everyone.
All right. So it's fascinating to know that 10% of our brain's neuron is what we know actually about, and we are drawing parallels into AI based on these 10%. The entire 90% is dark neurons. We don't even know what it is doing. But we also know that evolution has made everything play a role, right? If it is not doing anything, it will just not be there, right? But it's still there. That means it's playing some role, but it's just that we don't know what it is doing. It's there in the brain, it's silent. Either it is listening, like it's taking input, but it's not sending output. But either it's not listening, but just randomly spiking. So it's just doing one or the other, but it's just there. It is like when in the beginning, when they were finding about neurons and all, they never discovered dark neurons because the apparatus that they're using to find the neuron activity is sensitive towards just understanding the activation. So that's why these silent neurons were never discovered. It's later that they came to know, okay, there is a huge part of the brain which is silent, which is dark neurons. And again, there are a lot of hypotheses what might be the rule, might be the significance behind dark neurons, and that is like if you do an experiment over a lifetime, you might understand what these dark neurons are really doing, but no experiments run that long, right? So the idea is it could just do something for rare events. Like, okay, there's this running joke within the neuroscience community called Jennifer Aniston neuron. That is, it will spike only when it sees Jennifer Aniston's face. So those rare things, okay? So these are the things that probably dark neurons might do, may not do, I don't know. Maybe one of us will discover it, I don't know. So yeah, that's dark neurons. One more concept, which is spontaneous neurons. So what it does is, an individual neuron can spike without an external activity. So I've been telling that it will get inputs only then it will spike. I mean, when I say inputs, what we are seeing in the outside world, okay, those inputs. And that only leads to spike. But it is actually not true. All the concept, timer neurons, counter neurons, all of that is there, but that is not coding the information. Spontaneous neurons are coding information. Basically, the neurons in the brain are in a constant state of activation. They are always going to spike. There are two misconceptions. One, the external input is needed to, or is always the reason behind a spike. That is wrong. And second, only the previous neurons can activate this next neuron. That is also a misconception. The neuron can in itself get activated. And that's because our brain is a predicting machine. We have learned so much throughout our journey, right? So far, we know everything. So every time we see, I know this room, how it looks. Every time it's not coding how the room is looking. It already knows, right? So the brains have already formed the picture. It's already made the sense of it. So it's always activated. Only the change that is coming, that much is only encoded through the spontaneous neurons. So like these, only change is basically there is the information, only the change are adjusted. Are you getting what I'm saying? Yeah. So
But the change is also an input, right? Are you saying there is a change in the external environment?
yeah, so like when I'm going outside this room, I already know how it might be looking. So I'm not really like I already have a picture of it.
And the difference between your picture
Yeah.
and the actual
Yeah.
world would be coded by this neuron, or would be calculated by this neuron.
Yeah, spontaneous neurons are nothing but it's always spiking spontaneously. So only the change is basically carrying the information.
Okay.
Otherwise, timer neuron, counter neuron, all that concepts, yes, it's there. But it's not actually having the real information. It's just spiking, helping in spiking. That real
Real change in the signal strength, would that be or
Yeah.
whether it's activated or deactivated, that like 1 to 0
or new connections that are getting formed.
Okay, that would be.
That could also be achieved.
But it's
Yeah.
already active on it. It's constant in active state.
Yes. Yeah. So
Only when, suppose I have some preconceived things in my mind.
yeah.
So if I, as you said, the instance which you said, I already know when I go out, this is how it will look.
Yeah.
But as soon as I go, the tree might be this side, but later on it is this
Yeah.
side. So only that change is exists.
Yeah. So you don't have to code the entire thing.
So it's like a
That's how
transfer
your brain-
learning.
Already made connection there. Yeah. Okay, yeah. So basically this thing is the key to this question, that how are we able to have sub-second reactions when there are so many connections and loops in the brain? Wouldn't decision making in the complex circuits of the brain take forever? So there's the answer. It's always active, it's always predicting. You already have a predictive model in the brain. One last concept, we've been so far talking about neurons, but there's this other character in this entire story, which is changing the game, called astrocytes. And they are forming this tripartite junction. So the synapse, which is the presynaptic and postsynaptic neurons, there is one more thing that is there, and it doesn't happen always, it's there sometimes, called astrocytes. And what they do is, it's not a neuron, it's a different kind of cell within the brain. And what they do is, in this junction, the neurotransmitter that is released, it sucks into a little bit of that and keeps it with it. And one astrocyte has multiple branches. It can go to millions of other junctions and collect those information also at the same time. And the timing process of astrocyte is much slower than neurons. So it will have that information with it for a longer time, and it is capable of sending that information again back to neurons and things like that. So it kind of does, it's like a little bit of memory that is building. Okay, so, and this concept is a very new concept, very new. It was not there before. It's still, being experimented.
So this can then become the input for future excitation of other neurons, right?
It
And
could,
mood
yeah.
I mean, something like if you were to relate to emotion versus a mood, it will prolong the excitation or a particular state of the brain.
Yeah, so that could be a hypothesis which can be, tested, because this is a very new concept of astrocytes. It's still not fully discovered. But all we know is that it creates this tripartite junction, and it's possible that it kind of does that kind of thing that you're saying.
Because it's taking in some of the neurotransmitters,
Yeah.
right? Within
Yeah,
the
exactly. Yeah. Okay, now it is time for drawing parallels, and I'm seeing already you have connected dots. So what I'm going to do is because we don't have a lot of time, we are just going to take 3 concepts from AI, and you'll tell me how is it correlated with what we studied about neurons in the brain. Okay. So the first concept is of dropout neurons, where how many people here are actually well aware of AI and everything? Like, do you know what is dropout neurons? Okay, great. I can explain, but anyone wants to explain it?
Yeah, sure.
Go ahead.
So, should I sit or stand?
Anything.
Okay. So, basically, dropout is like when model is learning. So, basically, we shut down those neurons so that it doesn't get overfit.
Right.
In simple, but it's not a simple, but try to understand. Like, just like you say, she said that when the model is getting learned, sometimes it learns wrong things like the weights and biases, that the values, those values should be in some so that those values should be adjusted so that it learns correct things. And when we see that it's not learning correct things, we set some dropouts like 0.25% or 0.5%, and in output we can see the accuracy is increasing.
Right.
So
yeah.
basically that's my understanding of what
Great.
dropout
Yeah.
is.
Anyone wants to add anything?
Actually, you just want to maybe repeat?
Yeah, I'll just do that. Yeah, so dropout neurons, so this is basically a fully connected network where all neurons are connected from input to hidden to output. One-way connection, feed forward, and then there is backpropagation that happens. All of that is there, okay. And the model is learning. Now, when the models have learned, every weight is assigned for all these connections and everything is done, okay. But there is no flexibility when everything is assigned, right? So that's why randomness is needed. And randomness, one way of doing randomness is randomly shutting off few neurons in the hidden layer. Just randomly. We'll also not know which neuron is shut. So by that, at every pass of this learning, this is a new kind of an architecture in a way, right? So it has to relearn these weights. Okay, now this is not participating. So how do we, adjust the weights, right? So that way it's always like learning, and it is kind of generalizing, right? So that is why overfitting does not happen in the artificial neural network. And now can someone tell me how can you draw that parallel? Like, we learned something similar when I explained about the neurons in the brain, right?
You told about spontaneous
Spontaneous.
learning, when it takes a new environment या कोई भी नया change, so it is learning. So I feel when a dropout is done, so it is trying to identify a new possibility or new probability or what other things can happen. So I feel I could relate it that way.
Cool. Yeah. Any more connections?
The non-deterministic nature.
Exactly. Yeah. That is also a good answer. But yeah, that was the answer I was looking for. So the synaptic failure that we talked about, it prevents overfitting. So that's a parallel you can draw. That brain does this. Let's do that in the artificial neural network, and it actually improves the accuracy. The next, any doubts? Okay. Anyone? The next concept is transfer learning. I saw people already made connections there, but anyone wants to explain what is transfer learning first? Someone wants to take a shot? Yeah, go ahead.
So generally, in our neural network, all of the input, output, as well as the hidden layers are already formed. So when we want to adjust the model to our use case, we might have to replace the last or the second last layer to change the outputs according to our use case.
Right.
And that's where we add our own layer of neurons
Yeah.
to transfer the input outputs.
Exactly. Yeah. Okay. So what he's saying is that, let's say there is a generic data set. Now there was this ImageNet contest where the entire of huge image, different kinds of images were there, and the model was learned to understand this image, like image recognition. And there's this paper which talks about AlexNet. Okay. So basically there's a generic data set, and we have kind of learned the characteristics of this image, different images, and that's there. Now if we have a like generic data set could be literally all images, okay, and now a specific data set could be just differentiate between a boy or a girl, okay. So that is very specific. Now what in this case, it needn't learn the entire thing again. It has already, we can take a learned model which already knows the characteristics, okay. So we can take that, and just the last neurons, like he said, can be adjusted. Like only the new information can be adjusted to do the specific task, right? So this transfer learning basically is in a way predicting. It already knows a framework, and now we're just adjusting to the specific task. So what is this connection with
Spontaneous
the
neurons.
exactly?
Yes.
Yeah. Is everyone clear? Why is it spontaneous neuron? Yeah. Cool. Okay, one last concept, which is recurrent neural network. Now, we had a lot of feed-forward networks, neural networks like this, where there was just like this kind of connection, one-way connection. Later on, we also came up with recurrent neural networks, where this connection is fed back. There's a loop kind of thing, okay? And the idea behind that is it stores this memory. So especially in the case of text processing, in a sentence, we need the relation between one word to the other word. So that attention, like there's an advanced concept of transformers where self-attention and all is there. Not going to that, just putting in the words out there, but you realize there is a memory that is involved in the processing of these texts and all, right? So that is why that loop is formed. So if you, this is a representation of recurrent neural network, and when you unfold it, it's getting inputs, and it's also, this hidden layer is also communicating like this, and the output is also going to the next layer. So you see this kind of three connections, right? Where do you, it's very evident. Yeah, astrocytes, right? Okay, so here is the interesting thing, that so far dropout neurons, transfer learning, all that we saw, that was in a way, we learned from the brain and we are doing it in the AI world. But here, we didn't know about astrocytes before we came up with recurrent neural networks. It was like, it came up because, there was a task at hand that we had to solve for memory. So which is why these architects kind of tweaked with the neural network model, how can we introduce this, memory, and they tried creating these loops and all of that. And it is later that they were saying, how does brain really do this recurrent neural networks or transformers, like all of these things. That's when they came to know, okay, astrocytes connect these, like has this tripartite junction. So maybe that is doing it. So you see, it's not always one-way information that is flowing. Neuroscience is always not governing AI. AI is also helping neuroscience discover new things. So that is the synergy. And that's actually very exciting. So I'm saying it's a multidisciplinary field where you have so much to teach AI and you have so much to learn on the brain also, both ways.
So, would it be okay to say that this concept of astrocytes can be used to make training data sets more energy efficient? Because right now it's such a load on the environment, and so do you think this could be the solution for energy efficiency? That's a hypothesis.
I also had this hypothesis.
Oh, great.
Yeah, it's actually very interesting.
Our neurons are firing in the same way.
Exactly, yeah. So yeah.
Just another.
Yeah. I think we have covered the major all these concepts. Now the second part, before I have second part, I'll launch a second quiz. But yeah, second part is basically for you to just sit back and relax. I'm just gonna run few videos, but let's do this quiz. Same link, same code. I'll launch the second quiz. I'll just put one there. Yeah. Yes. Yeah. Yes. everyone there? I'll start the next question. Do you see the question on your screen? Yeah. What do you think does not help in learning inside the brain? Repetition, forgetting, reward, none of them. Pay attention to does not. Just 10 more seconds more, just finish off the answers. Alright, I will go on to the results. The correct answer is none. So repetition, forgetting, most of you got it right. Repetition, forgetting, reward, all has, in fact more of that. Emotions also play role in learning inside the brain. Now repetition, basically there is this saying called neurons that fire together, wire together. So every time if the same input is making this connection to the other neuron, then that connection becomes a strong connection. And that's why it's wired together. And that is a concept of Hebbian learning. You just make note of it and you can read it on yourself. Then forgetting. Now this is also very interesting. Again, new research that forgetting is very important for brain to actually learn. And that's because like there was, there's this interesting case. There was a Russian who had some problem in his brain and he couldn't forget. He had an infinite memory. And that really affected him to really learn. He couldn't learn anything. So that is why forgetting is also very important. With context, you have to adapt. You need to forget what is not necessary. That is also in a way saving energy of your brain. And it has a very huge role to play. Still not discovered by neuroscientists. A lot of people work on that. And there's also another interesting, not exactly related to forgetting, but this concept called catastrophe forgetting. So we can learn a lot of things together, right? When we learn new things, we don't forget the old things that we have learned. But when we take an artificial neural network model and make it learn some task and use that same model to learn some other, it will forget the old task that it has learned. The weights will adjust to a new task now. So it's not ready to learn multitasking and all of that. So basically this phenomenon is called catastrophic forgetting. It forgets what it learned before. So how do we really learn from the brain how we are able to do multitasking and teach the brain, the AI? So that's another thing that you can explore if you're interested in that direction. Reward, it's a huge another discipline called reinforcement learning. So yeah, reward is also very much there. Emotions are needed, so much more. But yeah, here the interesting thing with forgetting is also needed. Everything has a role to play. I'll go back to sharing my screen. Because we don't have time, I have like few videos, but I'm going to share those links. You can watch it on your own. We'll just play one video. So our brain, the kind of decisions that we make, right, the conscious decisions are just 0.some%. 99.99% of decisions that we make are by the non-conscious processing or the subconscious brain. So our brain is always active, that is there, but we only know the conscious, that percent, that is just like tip of the iceberg. The entire is actually non-conscious processing that is happening inside the brain. So how do we harness the subconscious mind? So there are like a lot of things you can do, but there's this one exciting thing which I'm going to show through a video. That's one way of thinking about it. The sound is...
They say the eyes eat before the mouth can taste, telling the brain deliciousness is on its way. But why do we burn our head out with countless hours of mind-numbing scrolling as it goes through menu after menu every day? 132 hours a year to be precise. Psychologists call it choice overload. a state when the brain is faced with an overwhelming number of options and struggles to make a decision, often ending up making the wrong call. Hunger Station, the leading food delivery app and spicy innovator, wanted to ease this pressure and help people make the right choice with a smarter way to order, using the power of the subconscious mind. The first ever online food delivery order placed by your subconscious mind. Because it's way more powerful and can process things 500,000 times faster than the conscious mind. We decided to let it do the ordering. A feature on the Hunger Station app recognizes you've been hopelessly scrolling and launches the intuitive tool. A number of mouth-watering cuisines are displayed as the camera meticulously tracks the eye's interest using advanced algorithms and the front-facing camera. A smart AI uses proprietary food topic modeling to narrow down the options and presents a data report of what the eye concentrated on the most, or what the subconscious mind is craving, giving the user a list of relevant restaurants to order from. This innovative and intelligent feature caught the eyes of the media. We even mirrored the experience on social media, giving every Saudi the opportunity to harness the power of their subconscious. And soon, subconscious ordering became a thing, leaving us with a banquet of new data for more accurate and personal targeting in the future. By helping Saudis awaken their subconscious mind to ordering the food they love, we gained a cozy corner in their conscious mind for years to come.
So this was also, it's not our work, but this is a kind of work I was also doing in my previous team. So understand the non-conscious brain, that is also there. I'll just throw the concepts, but you can watch the videos. I'll share the PPT with you later on. But this person called V.S. Ramchandran, he played a key role in inspiring me in this field. The very first book that I read in neuroscience was Phantoms in the Brain, which was written by him. And he also has a lot of other concepts. Definitely you should pick that book and read it. It's a must if you're inspired by this particular session.
What's the name of the book?
Phantoms in the Brain. Yeah, and he also has a lot of theories on neuroaesthetics. So if you're a front-end developer or something, you should check out neuroaesthetics. There is a video also which I'll right now not play, but I'll share the link. Then there is neuromorphic engineering. So in case you're a hardware engineer or you're working in this direction of how to save energy and all that, then there is this discipline of neuromorphic engineering that you should really pay attention to, because brain just runs on 12 watts, right? But deep mind and all that AlphaGo is taking how much, right? There is so much energy issues and everything. Brain is a green energy resource, right? So how do we really understand how brain is doing so much energy efficient? And this cortical labs, very exciting, very cool, very cutting edge work they're doing. They are basically through stem cells, they're creating these neurons, and these soft tissues are integrated with the hardware silicon. And when these actual neurons fire, it's also communicating into the hardware. So it's taking neuromorphic engineering to the next level. Neuromorphic is what learn from brain and then do it. But here they're integrating it both together, and they have made that system play ping pong ball also. So it's really cool. And then there is neuroplasticity. You had mentioned that. Again, David Eagleman, he has really cool work in that. You can check out the video. It's a short video, but you can check the longer video. He has a TED talk also. So with this, I will end my talk. There are a few resources. If very particularly interested in computational neuroscience, then I would recommend doing this summer school called by Neuromatch. I had done it like 3 years ago as a student, and then I did it as a teaching assistant also. But that is a really cool space, really good community, and then and it's non-profit. There is a Coursera course, computational neuroscience, by this professor from University of Washington. Really good course, very heavy, but take your time to really go through it. Then DeepMind has this paper called Neuroscience Inspired Artificial Intelligence. It also tells you a lot of these connections between neuroscience and AI, and these books to begin with. But I have a huge list of books. You can pick me whenever you feel like you have exhausted this list. Phantoms in the Brain that I mentioned, David Eagleman's book, Live Wired, there is a basic book called Brain. Models of the Mind by Grace Lindsay takes you the history and also tells you in great detail how this neuroscience and AI relationship is there. Similarly, The Deep Learning Revolution by Terence Sajnowski is a really excellent book. So yeah, with this, thank you so much.
Okay, so I think we have time for about 3 questions, and then we can move on to coffee and biscuits and all of that. And I mean, Kartika's around, we're going to catch her and keep chatting with her. But if you have any questions?
Yeah, go ahead.
Firstly, amazing session and really well connected the two drinks. So
Thank you.
appreciate that and explained in a very basic manner. One question is, what exactly did you do at Cerebral and Fractal? What is the work?
Yeah.
And what is this field of computational neuroscience about? If you can just
Yeah, for sure. I can tell. I hope I don't, go against the compliance of Microsoft by sharing my work from Cerebral. But just giving a glimpse, so what we did was Fractal is a consulting company. So there, obviously, we are powering human decisions at the enterprise, and it's again understanding the non-conscious processing. So when we see visual stimuli, how the attention is really working. Covert attention, there is overt attention. So just trying to understand, our main role was visual stimuli. So we were studying the visual stimuli and how the decision making inside the brain happens. And the finding is, it just takes 960 milliseconds to process a visual stimuli. So
and so you actually also needed the neuroscience knowledge as
right,
well, right?
yeah, it was a very multidisciplinary team. So that is how significance of multidisciplinary team. Like, I really want to push everyone to be in this space where you can connect people with different disciplines, right? You have so much to learn from each other. So we had person from neurobiology, biomedical. Then we had a designer who was coming from the neuroaesthetic point of view. I was from the AI, and there was a hardware person also. So it was a multidisciplinary team. We were all just brainstorming every day. That was our activity. Yeah.
And so it used to be the hunger station kind of real world application.
Yeah.
To come up with.
Yeah. It was research. Yeah.
Let's just maybe move to the next question.
Yeah.
You can catch her later.
Yeah.
Anybody else?
Hi, I'm Harshit. Actually, I'm a software developer, but I don't know about neurology and everything. But usually I use ChatGPT for getting some answer.
Yeah.
So I'm relating to that, like what you're saying.
Yeah.
That they're connecting the dots and everything. So the question is, like, there is a one fluid in the mind, dopamine. So
Neurotransmitter. Yeah.
it is a neurotransmitter. So what is the connection of neurons and dopamine?
So we saw these neurotransmitters are there, right? So dopamine is a type of, like serotonin, there is dopamine, which is also a neurotransmitter, and that communicates information between two neurons, and it gets activated when this reward learning, when you studied reinforcement learning, right? That time this reward prediction error is coded by dopamines in the brain. I'm just throwing words, it's a huge concept explained, but yeah, you can look it up.
Okay, guys, one last question, if anybody has.
Yeah.
Hi, it was a nice session, and I want to ask you, is there any research going on in the field of emotional artificial intelligence? Because I know one professor who is working on in that field.
Nice.
He is doing his PhD. So if you could just suggest some things.
Yeah, that is a huge. I
Yeah.
had a slide on that. Then Shaina made me like, it's too much content. Remove it. So yeah. So emotions, very debated topic. But there is empathetic AI, right? Like, how do we understand emotion? That was also part of what I used to do in my previous work. And this book called How Emotions Are Made by Lisa Barrett, you could pick that book, and it kind of demolishes all the notion that we have about emotions, and it tells through experiment that what she understood about emotions. And there's so much work is happening, but
So are there any models that are being created
Empathetic.
for this, like artificial emotional intelligence? Something like that?
not there fully. It's still in research. Yeah.
Okay. Thank you.
Yeah.
Okay, guys, maybe we'll wrap up here. Kartika's around, you can move to the cafeteria and just chat some more.
Thank you so much for coming. And if there is an interest in learning more about this field, Kartika is leaving, but maybe we could do an online series with her. So please let us know if you'd be interested in something like that. So just wanna just back up.
Yeah.
So just to wrap up this session, again, thank you so much everybody for coming and being here, and a huge thank you to Kartika. I will repeat again, just to summarize. So Women Who Code, the idea behind this community globally is to help women succeed in technology careers. And so if you guys want to be a part of this community, there are QR codes all over this room. Please scan them or get in touch with one of us. You can just be a member of the community, or you can be an active volunteer. We'll walk you through and help you figure that out. Let us know how we can help you as well. So reach out to me and Shaina and tell us what resources, skills, sessions you would need or feel like would benefit you. Yeah, I will end here. Let's maybe move to coffee. Thank you guys so much.